Good morning everyone. This is Swapna. Today's our topic in machine learning is version spaces and candidate elimination algorithm. The candidate elimination algorithm that addresses the several of the limitations of the find S algorithm. Find S algorithm which is used in machine learning to find out the hypothesis. So it covers the several limitations of the find S algorithm. And what is the main key idea in the candidate elimination algorithm is output is the description of set of all hypotheses consistent with the training examples. It gives the set of hypotheses which is consistent with the training examples, and also it provides the conceptual framework for introducing the several fundamental issues in machine learning. And this candidate elimination algorithm has applied to the problems such as learning regularities in chemical mass spectroscopy and learning control rules for historic search also. The practical applications of the candidate elimination algorithm and find S algorithms have the similarity in one situation, that is one factor: they both perform very poorly when the given noisy training data on the when it is given to the noisy training data, these both algorithms perform very poor. This is the similarity between the candidate elimination algorithm and find S algorithm. Candidate elimination algorithm solved some issues which are faced with the find S algorithms. In that, one thing is it covers the positive training examples as well as the negative training examples. Here we are giving the what is the representation of the candidate elimination algorithm and definition. Here definition is: a hypothesis H is consistent with a set of training examples if and only if H of x is equal to C of x for each example, for each training example which is present in the D. For that, notation is given like this: consistence H comma D. H is the hypothesis, D is the set of training examples for all ordered pair of x comma C of x. In this, x is the instance of the training example, C of x is the target concept of the training example, and these two belongs to the all the training examples. And if and only if H of x is equal to C of x. What is H of x is the target concept of the hypothesis, and C of x is the target concept of the instance. So here they are using the consistent word. The main difference between the find S algorithm and candidate algorithm: find S algorithms uses the word satisfies for hypothesis. That means, what is the meaning of satisfy hypothesis? Means whenever H of x value is equal to 1, that is considering as a satisfies hypothesis. And here in candidate elimination algorithm, using the word of consistent. What is the correct meaning of consistence related with the hypothesis? Means this hypothesis mainly depends upon the target concept. Whenever H of x is equal to C of x, then only we can say as a consistent. So in candidate elimination algorithm, it gives the set of hypotheses which are consistent. That means it must be the H of x is equal to C of x. So candidate elimination algorithm represents the set of all the hypotheses consistent with the observed training examples. This subset of hypothesis we can call as a version space. On the heading we specified version spaces and candidate elimination algorithm. Till now we known about the candidate elimination algorithm, what it covers that we studied till now. And here we are giving the definition of version space. What is version space? Means subset of hypotheses. So that we can call as a version space. For this exact definition, here we gave in the here. What is the definition? Means the version space denoted by Vs. Vs represents the version space, and H comma D. In this, H is the set of hypothesis, D is the set of training examples. Here version space is the subset of hypothesis from H consistent with the training examples in D. That is represented with this notation: Vs H comma D is equal H, small h belongs to capital H, consistence H comma D. Small h is hypothesis, capital H is set of hypothesis, and capital D is the training examples. So this is about version space definition and candidate elimination algorithm. So here to get that version space contains the subset of hypothesis. To find out that, here it follows the one algorithm. That algorithm name is the list then eliminate algorithm. For this algorithm, they 3 steps are there. First step is to get that version space in that subset of list. First step, it considers all the list of containing every hypothesis which is present in the capital H. Already we know capital H is set of hypotheses. In this first step, what they are including all the hypotheses which are present in the capital X. Second step, for each training example is represented with the ordered pair of x comma c of x. For each training example, it removes from the version space any hypothesis is satisfying the condition of h of x not equals to the c of x. If h of x is not equals to the c of x, that hypothesis it removes from the version space. Remaining all it keeps as it is. That at last step, what we get the list of hypothesis in version space which satisfies the consistent condition. So this is the list then eliminate algorithm to find out the version space. By this algorithm, we can find the version space. And here we gave some example of version space, how we are getting, what is the final version space we will get. So generally from the machine learning, from the concept learning concept, we are using this continuously one example, that is enjoy sports, with the 4 instances, that is with the 4 training examples. We are giving the explanation for the enjoy sports. So this is the final version space for the enjoy sports with the 4 instances. So first S is the one representation of hypothesis. This is specific hypothesis. G is one more representation of hypothesis. G is the general hypothesis. In between this, we are having the 3 hypothesis, list of 3 hypotheses. This subset of hypothesis we are calling as a version space. At the final stage, after the candidate eliminate algorithm applies and list then elimination algorithm applied on the enjoy sports, we will get this subset of hypothesis which is like this. This is the version space. This is the one example for version space. By using which type of training examples we are getting that output means these are the table. Here I am giving the 4 instances are there with the 6 attributes and 1 target concept. Excuse me. In this, which target concept value is having S means that we can considering as a positive training example, and target concept value is no means it is considering as a negative training examples. I said candidate elimination algorithm applies for both training examples, positive and negative training examples. Whereas in find S algorithm only considers the positive training examples and it ignores the negative training examples. So to represent the version space, in that figure also is used the specific some specific hypothesis and general hypothesis, that we can call as the general boundary and specific boundary. General boundary is represented with the capital G of version space, and VSHT version space is represented VSHT. It is a set of its maximally general members, and specific boundary contains maximally specific members. In between this, every member of version spaces lies in between these 2 boundaries, between the general boundary and between the specific boundary. General boundary is represented with the specific boundary is represented with the capital S, and whatever the members or hypothesis in between these 2 boundaries, that we can call as a version space. So next one is the candidate elimination algorithm. So every algorithm is a bunch of steps or set of steps to represent the one process, to complete the one task, whatever the steps or what are the bunch of steps we are using in the sequence, that is we can call as a algorithm. So candidate elimination algorithm is represented like this. For this, generally it uses the 2 hypotheses, that is maximally general hypothesis which is present in the H, that is represented with the G, and maximally specific hypothesis which is present in the H is represented with the S. So to apply this candidate elimination algorithm on the training examples, it will start with the 2 hypotheses, with the maximum general hypothesis and maximally specific hypothesis, and to continue on all the training examples, on the set of all the training examples, and finally we will get the specific finally we will get the hypothesis, set of hypotheses which are consistent with the training examples. To get that, it is using these two hypotheses, general hypothesis and specific hypothesis. And every time whenever going through the training examples, depending upon that positive training example or negative training example, general will become as a specific and specific will become as a more general. Every time we are on that, depending upon the every training example, we will converting the more specific to the generalized one, and more general hypothesis to the specified hypothesis. At last we will get within the boundaries what are the set of hypotheses which are consist with the all the training examples. So in this candidate elimination algorithm, we said initialized step is we are taking maximum general hypothesis and maximally specific hypothesis. After that we are going to the training examples. If the training example is positive training example, positive training examples removes from G any hypothesis inconsistent with the D. Already we know what is the consistency. H of x is equal to C of x. If it is inconsistent, then remove from the G. And for each hypothesis S in capital S that is not consistent with the D, remove S from the S and add S to the minimal generalization H of S. H is consistent with the D, then add some member of G more general than this one. Remove from the S to hypothesis. So what is the meaning of these steps means, if it is a positive training example, we are keeping more general specific, more general maximally specific general hypothesis is keeping as it is, and we are changing the maximally specific hypothesis to making it as whatever the attribute values are present in that positive training examples, depending upon that we are making it as little bit generalized. Like that, for every positive example we are continuing like this. If we encountered with the negative training examples, then if we encountered with the negative training examples, what we are doing, we are keeping specific hypothesis. Specific hypothesis is like that only, and we are making more general hypothesis to the specific hypothesis depending upon the attribute values of the negative training example. Depending upon the attribute values of the negative training example. Is that clear? So these are the steps given like this in this candidate elimination algorithm. To understand this, we are going with the training example. We are going with the example of enjoy sports, which is having, till now only we saw that table, which is having the set of training examples positive and negative. That is 4 instances are there. In that 3 are the positive training examples and 1 is the negative training example, and we are applying the candidate elimination algorithm on these training examples here. So this one is the our enjoy sport example. So I said 4 training instances are there. In that S, which is having the target concept S, that we are considering as a positive training example, and which is specifying as a no target concept value, then we can considering as a negative training examples. Depending upon the steps, every step we are need to finding. So on that first step I said we will start with the most maximally specific hypothesis and maximally general hypothesis. So this is the maximally specific hypothesis. On the first step we are indicating with the S naught, which is having the all the null values as the attribute values, which is having as all the null values as the attribute values in the first step, that we can considering as a maximally specific hypothesis. That means it won't accept any attribute values, it won't accept any attribute possible values. From that we are making, depending upon the training examples, we are making it as general, and on every step of training examples. If it is a G naught is the maximally general hypothesis. It contains all the question marks as the attribute values. That means it accepts everything. Whatever may be the possible value of attribute in that training examples, it accepts that one. That's why in positive training examples, we won't change the most maximally general hypothesis. That's why how it is moving, how it is changing the values of S naught and G naught, that are we are represented with the arrow marks. Whenever the positive training example we encountered, S naught will become as a S1 and G naught will become as a G1 with all the same values. If any negative training example we are going to encounter, then G0 changes its attribute values to the next step, and S0 moves to the with the same values to the next step. So that is about the candidate elimination algorithm. So first step we completed with the maximally specific hypothesis and maximally general hypothesis. Next we are starting with the training examples. So consider the first training example. First training example, here we are represented, here we are given as a first training example. First training example, target concept value we are having S, means it is a positive training example. So what are the attribute values? Sunny, warm, normal, strong, warm and safe. Warm and same. So we are changing positive training example, this one we are encountered, that's why we are changing maximally specific hypothesis into the next one, making it as general. To make it as general, all the null values are replaced by the all the attribute values of first training examples. So S1, it make from S0 to it may we wrote the S1 little bit more generalized one, comparing with the S0, and the all the null values are replaced with the attribute possible values. So after that G0 will become as a G1 with the same values, because it is a positive training example. Second, after this, once again in the second step we are continuing with the next training example. What is the next training example? What is the value of target concept of the next training example? Is this one is also S, means this is also a positive training example. This is also a positive training example. So these are the attribute values. So we will compare these second instance attribute values to the S1. So after this S0 by the first training example, what is the hypothesis we got? S1 and G1. G1 is having all the question marks, that means it accepts all the possible values, so no need to change G1. So after the training example 2 also, G1 will become as a G2 with the same values, and now we are changing from S1 hypothesis, or once again we are making as more generalized by using these attribute values, by comparing with the attribute values of the second instance. So compare the first attribute value with the hypothesis which is the specific hypothesis, sunny and sunny in the S1. So that's why we are keeping the same attribute value in the S2 also, sunny. Second also we are comparing warm and warm, we are keeping as it is warm. Third attribute is here it is a high and here it is a normal. Here it is a high and here it is a normal. Both are having the target concept value S, that means it accepts the both. So replace these attribute value with the question mark, which will accept the two possible values, Next, comparing with the second instant, fourth attribute strong. So we are making same thing. Next one warm, we are keeping as it is. Next one is the same and same. So by these two training examples which are having the target concept value S is completed, that means these H of X, these hypothesis target values also S, that means by these two training examples are consistent. This set of hypothesis, comparing with the training examples, these two are consistent. Next we are going for the third training example. What is the third training example? What are the attribute values? Means here it is. This is the third training examples. This target concept value is no, that means it is a negative training example, and these are the attribute values: rainy, cold, high, strong, warm and change. So we encountered with the negative training example, that's why we are keeping the same more specific value as it is with the same values which are present in the S2. So S2, what are the attribute values are there, that now it become as the S3 with the same attribute values. And whenever we encountered the negative training example, then we are comparing that with the training example attribute values and with the specific hypothesis, and we will write the generalized specific hypothesis. Here it changes generalized specific hypothesis from one hypothesis to more than that, depending upon the attribute values. See, we are checking that first attribute value in this training example, third training example, rainy, and here it is the sunny. Both are different, that's why we are writing one hypothesis with the remaining attribute values as the more generalized value, with the attribute value which is present in the positive hypothesis, positive training example, or whatever the hypothesis we most specific hypothesis attribute value is there, that we are writing sunny and remaining all question marks. Next we are comparing with the second attribute cold and warm. That's why these two are also different. That's why we are writing with the warm attribute. First one is in question mark, remaining all attribute values also we are keeping as it is, and second attribute value with the warm. And next one is the third attribute value, strong and strong. Strong and strong both are having the same. That's why no need of including the hypothesis here in the general to specific one. Next also comparing warm, attribute value is the warm, and here also attribute value is the warm. No need of including that one. After that once again it is changed, last attribute value same and change. Once again we are writing the one more hypothesis, making from more general to the little bit specific by using this attribute value. So these are all question marks, and last one is same. So by this third training example is also completed. Now we are having the S3 specific hypothesis and G3 general hypothesis. So next we are going for the last training example, which are in our set of training examples. This one is also having the target concept S. So all the attribute values we need to compare with this S3, and we are writing the more general one S4. Sunny we are keeping the same attribute value in S4 also. Warm we are keeping the same attribute value in this warm also. Next one is the question mark, and here high in these two, which one is the more general means question mark, so we are writing the question mark. Next one is the strong and strong, so we are keeping the same attribute. Next one is the warm and cool. These two are different. To make this attribute value as the more general, we are replacing these attribute values with the question mark. Next one is also same and change. These two are also both different. That's why we are replacing this attribute value with the more general one, question mark. So by last training example, we got the more specific one is sunny, warm, question mark, strong, and two question marks. Now we are going for the generalized one. Generalized one hypothesis containing the three hypothesis, and fourth training example is also positive training example. After this there is no training example. That's why we are comparing these three hypotheses with the S4, and we are checking it is having the sunny and sunny, so this is equal. That's why we are writing the same thing with the same we are including this hypothesis into the G4. Next we are comparing with the second attribute warm. Here it is also having the same warm, and this one also we are including to the G4. Next one is the strong. There is no strong attribute, no need of once again writing. Next one is the question mark and question mark. Here one more hypothesis is there with the last attribute value same, and here it is the general one. So if you want to write it, make it as a general one. If both are having the same value means we will write our same hypothesis and we will include into the G4. If these two are both are different means we need to replace with the generalized one. We need to replace with the generalized one or positive training example possible value. What is positive training example possible value for this last attribute is means question mark. Then we will get this type of maximally generally hypothesis. No need of writing that one, because every time we are changing maximally general to the little bit specific, so no need of write, no need to include that one. Last one, now boundary will contain these two hypotheses. S4 is one type of specific boundary, G4 is one type of specific boundary, and these are the hypothesis specifically and general one. We got this after the candidate elimination algorithm, after the applying the candidate elimination algorithm, but we need to get the set of hypothesis, subset of hypothesis which will consist for all the training examples. Here we are getting these three only, but this one is more specific, this one is more general. In between this, by using these two, we will write the in between hypothesis, which will is subset of all the hypothesis as well as consistence So in this last slide we are showing that one. This is the final version space of the Enjoy Sport concept learning problem with the training examples described earlier, and these are all consistent. How we are getting means by using these two hypotheses. By using these two hypotheses, we are getting this one. By the G4 hypothesis as well as with the S4 hypothesis. S4 hypothesis specifically constraints are containing sunny, warm, strong, remaining all question mark. So by using this G4, sunny it is containing, it is not containing any other one, remaining all it is represented with the question marks. So it will take sunny and any one of these two, sunny and warm or sunny and strong. So from this sunny and by using this strong it wrote this type of subset. Next also sunny and warm is also possible, so it will write once again this more type of hypothesis. And here one more hypothesis is there. So warm already here, so warm already here it is covered in this hypothesis also. With the warm and strong it is making the one more hypothesis. So these are the subset of hypothesis. This we can call as the version space. These are all consist with the these three possible hypotheses are consist with the all the training examples. Now this is our actual output after the candidate elimination algorithm and list then algorithm applied. That's why we are included and we are removed, which is not consistent, and we got the this subset of hypothesis. This we can call as a version space, final version space. By this slide I am ending this topic today. Thank you.